Alright, so today's lecture is called A Linear Map of the World Wide Web. What have we done so far? We've done some stuff, who cares? Last class we did Lavat's local lemma and the resampling algorithm. That was fun. This class we'll be talking about the page rank system that was used to kind of rank search engine results. But I'm really using this as a vehicle to introduce quite a number of real topics, probability subjects. So we'll be talking for the first time about random walks. We'll be talking about stationary distributions of random walks. And in particular, we're going to probably spend a while trying to prove this thing called the Perron-Frobenius theorem, which just tells you everything you need to know about random walks and stationary distribution. That's the really important part. Okay, so this, I guess, was a picture from Wikipedia of the World Wide Web, some small part of the World Wide Web. So I don't know if it's a very interesting one. So I guess in the center there's Wikipedia, and then there's like links to other web pages uh, around the world, roughly by domain. Um, this is obviously a very small subset of the internet. Yeah. All right. Probably the web internet's probably older than all of you, so I don't really need to explain it too much. All right. So a search engine takes in a search query, and it's supposed to return websites, right? Okay, so what's the first thing, maybe the first task of a search engine is somehow to like go through and just like download everything and index everything so that if you look up some word, give me any word. Huh? If you give it the word internet, you could find a lot of pages that are supposedly contain the word internet probably, right? So maybe the first task is just this kind of trying to figure out what are the relevant web pages at all, sort of just from an organizational and searching kind of standpoint, just retrieving. Okay, and maybe some of those data structures that we've done earlier, like approximate nearest neighbors or something, may be relevant for some of these tasks. Okay, but there's a second question. See, if you ask Google for returning web pages that contain the word internet, you're going to get a lot of web pages, right? So the second question is, what are the most relevant of these web pages? Okay, so, well, maybe internet's not a very interesting query. So if you had a more interesting query, such as, well, let's say you're doing one of our homework problems and you search, how does Johnson Lindenstrauss preserve the dot product or something, right? Um, there may be lots of web pages out there that contain the word dot product and random projection and stuff like that. And, which of these are dubious and bad proofs and which of them are actually going to give you something short and simple that you can copy and not cite. What are the better ones? Okay. So, this is really, we're interested today in this second question, not of just like organizing or downloading the whole internet. We're interested in the question of ranking web pages. Okay? So I wanted to open this up to ideas because there's many possible ideas out there and people are still generating ideas, right? So in general, how can we rank web pages? Okay, some kind of popularity, great. But how do we measure then popularity? We need to ultimately come up with something relatively simple and quantifiable that we can turn into a program, right? Yeah. Okay, so I can say how many other pages point to this website. Okay, in fact, that is going to be kind of coming up on the next slide. But before going there, I could still solicit more ideas. So that's a very good idea. But in particular, what kind of one essence of this idea is taking advantage of the link structure of the website, right? So we're not just analyzing websites on their own, looking for particular words that appear in the website. We're actually looking at how the websites relate to each other, and we're hoping that actually the structure of the World Wide Web altogether actually contain a lot of information about maybe the popularity of the websites. Okay, so one idea is to count the number of incoming links or something like that. Any other ideas before I? Yeah. Oh, okay. So, yeah, maybe at a secondary level, I guess that's maybe slightly beyond the scope because that requires more data than this question was immediately asking for. But it is true that every website out there is going to track all your clicks and gradually realize what cat pictures you're particularly drawn to, and then you only get served cat pictures, right? So, okay, there's some of that too, but that's slightly beyond the scope because you'll need more information from the user. Okay, so let's start with this idea. Okay, so I'll call it. We'll proceed to develop a sequence of kind of scores. Okay, so we're going to think of websites as vertices in a directed graph. Okay, so a link will give you a directed edge. So the first proposal, score 1, is counting for a vertex v the number of edges going into v. Okay, so that's the number of other websites that are linking to v. Okay, so that's very natural. Okay, how can you break this system? Yeah. Yeah, or okay, if you wanted to promote your own website, like I wanted to promote my own web page, right? Nobody's reading my papers. I want to promote my web page, so uh, I'll make a billion fake academic websites, all pretending to read my paper by linking to my website or something, right? And just artificially increase my score. Okay, I'm not saying people do that, but okay. So one issue is this. This makes sense in the sense that okay, we do think that a website that gets more links ought to be better. Except you can make fake links rather easily, right? So this is sort of like at some level unbounded and kind of easy to hack. Okay, so we can make a lot of fake websites and stuff like that. Uh, Let me also point something else out. Um, okay, so how would I say? All right, let's say you had two lists of the best movies ever. Okay, this list is called Top 10 Best Movies Ever, and this list is called Top 100 Best Movies Ever. Which list would you rather be in? A top 10, right? Top 10 seems more prestigious because that list is kind of giving out less points than this list. Okay, great, you're top 100, but here you get to be top 10. So, and maybe another thing about this is that if there's some website U that has tons of links, this is supposed to be a picture of tons of links, 6, okay? It's giving out tons of points, right? And whereas another website, only has 2 links or something, but maybe you would assume they're more careful because they're not just giving away links to everybody. Okay. So, all right. So if I wanted to maybe first address this issue, which is that at some level, uh, the same 2 websites can sort of give out way different quantities of points just by having more links, and thus one website can be much more influential than another on the overall scoring. How might I try to correct that? Yeah. Yeah, we can divide it evenly. Okay, so if you're in the top 100, you get 1/100th of a point. If you're in the top 10, you get 1/10 of a point. Okay, so that'll bring us to idea 2. Okay. All right, so now each website can only give out 1 total point. So at least you can't just like make tons of outlinks. But there's still that other issue that came up earlier, which is how do we deal with all these kind of fake websites, right? That really don't matter, but are still affecting scores. Sorry? Yeah. Okay. So I have some. Okay. So yeah. So at a high level, I have some really lame website U that's giving away points, and I want to try to figure out that view is lame. And so you said, oh, I can try to see how many point to you. Okay. So maybe if I had some other scoring system to figure out uh, if you ought to be giving out many points or something. So maybe like a secondary set of weights even, right? Okay, and now I sort of have the same problem all over again, sort of, right? Because yeah. So I think that's a good idea. I think that maybe if I understood which websites were already respectable, then I would value their outlinks more. But I'm doing that for the sake of addressing this question of identifying which of the websites are respectable. Yeah. Okay. So this whole like I want to weight the authority by the authority or something seems circular, right? Except in computer science we can deal with circular stuff because we can do recursion. Okay. So not quite recursion, but we can potentially have cycles. Slightly different. So okay, here's a third idea. I'll define score 3 of V, okay, as now each website is weighted by its score 3. So whatever its score is, that's how many points it can give out, and it'll give it out evenly. Okay? So this has a very nice sort of self-consistent feel to it, right? It's only the high authority websites that can bestow authority to other websites, and there's some kind of equilibrium, right? Okay, so this is a good idea. All right. Okay, so all right, so this is relatively flawless, but I would say maybe there's one technical issue. Uh, so it's quite clear that how to compute score 1, score 2. But what about score 3? So score 3 looks good, right? I mean, the idea that, oh, sort of everything should be in harmony like this is very appealing, right? But yeah. Okay, that's actually not, okay, so the idea is, oh, can we just kind of like start with anything for score 3 or use score 2 because that seems like a reasonable and iterate or something. As some of that, at the end of the day, that might be what we do, yes. But I wanted to first point out, it's not clear that score 3 exists, right? Here I'm requiring score 3 to satisfy a bunch of equations. So it needs to satisfy this for all v, right? So as nice as score 3 looks, it is not at all clear that there exist values that make all these equations come true, right? So this is to keep in mind, this is for all vertices. That's the first point to address. And if it doesn't exist, there's nothing to try to calculate as well. Okay, so that's really the big question. Why should there exist values that satisfy an otherwise very appealing system of equations? Okay, so that's the question. Uh, any shots in the dark as to why? Yeah. Oh, okay, so there is an all zero solution, but somehow that's not very interesting. So I guess what I'm saying, what we really want is a non-zero set of values score 3. So, okay, why should there exist a non-zero set of values? I should have written that. Not all zero. Right? Yeah. Um, could you? I guess you could, but maybe one thing maybe worth trying then is what if I gave you guys a simple example then? All right, so let's take a graph that looks like okay, maybe just a simple triangle that's going around in a circle. Um, okay, so there is this nice harmony of kind of ingoing goes outgoing. Uh, mm, I would say that's neither right nor wrong. It's kind of there, but it's not exactly the perspective we'll take that'll make it clear what's going on. Okay, but okay, just for fun, I'll make it a little more interesting. All right, here's a four vertex graph. Can we come up with a set of values for these four vertices that match this equation? So the out degrees are all like one or something like that. It's not too tough. Yeah. Okay, so if this was like some value one, that can't possibly be because there's no kind of value coming back to it, right? So we know that kind of value going out has to be equal to value coming in. Okay, so this is definitely zero. Okay, so leaves in that sense, or ones that only have outgoing edges, will always have value zero, which is probably ideal from a web page ranking point of view. Okay, so all that's left then is, so this is basically irrelevant. All that's left is this triangle. Well, so at some level in a graph like this, all the vertices are the same, so they must get the same score. So let's just try one for each. Okay, so all right, one goes in, one goes out. That, okay, that's fine. Um, what if we made it a little bit harder? I don't know the answer to this, but surely there's an answer. All right, what if I added one more edge so it's not totally symmetric? Well, so we want to know if there exists some value of score 3 that sort of doesn't change, so to speak, right? If there's just something satisfying a system of equations. Oh, okay. Let's see if that works. Okay, if I did 1/2, 1 and 1, uh, okay, so it looks like, okay, so we can annotate kind of how many points go along each edge if this was like the equilibrium. So for example, from the top, 1/2 would go down along this edge because there's only one edge leaving the 1/2 going down. Um, and then 1 would always be going this way because that's the only edge leaving the vertex is weight 1. And then up here we would get 1/2 and 1/2. So it does seem like this works, huh? All right, well done. I had no idea. Okay, great. All right, so that would be the solution then for that graph. Okay, so we know that maybe for some small examples, it's possible. That's of course obviously not a proof. Also, uh, although we got saved by one of your peers, uh, it didn't seem very easy to solve the triangle plus one edge. Like you probably tried a couple values, or maybe this first one you tried because it's simple enough. Okay, but it's not as obvious as the original triangle that maybe they should all be equal. Now imagine there's, God forbid, 5 edges, 6 edges, n edges. Okay, so all right, so here's the theorem we're going to prove. So first, just some notation. So this delta to the v is going to show up a lot. This is going to refer to non-negative vectors with one coordinate for every vertex that sum to 1. Okay? You could think of that as like distributions over the vertices. Okay? Because they're all non-negative values, they sum to 1, so it's like randomly choosing a vector. Okay, so with this notation, our theorem is that there always exists, no matter what, vector x satisfying this system of equations. Okay. All right. Okay. So that's really what we're going to try to prove today and come to understand. Okay. Oh, there's more to the theorem. If G is strongly connected, a strongly connected graph, then actually x is unique and the values are strictly positive. Everything will have positive weight. Okay. Before we got 0 weight because that was a vertex that just pointed in, so it wasn't strongly connected. Okay. Any vertex that doesn't have anything coming in will always be 0. Okay. And now I guess the real question is why. Okay, so no ideas why, right? All right. So what's actually going to clarify this is taking a perspective based on random walks. Okay, so what's a random walk on a graph? So you're at a vertex. It has 10 outgoing edges. You pick one of them randomly, and you go to that vertex. Okay, so U has some edges. We'll pick one of them. We'll go to a new vertex U2. And next step of the random walk, we have some edges. We pick one of them uniformly at random. And we go there, and so forth. Okay, so just random walks, just picking random edges. Now, after you take 100 steps, it could be in many different places. And there's some kind of probability vector, right? What are the odds of being at this vertex after 100 steps? That vertex, that vertex. The question is, as 100 gets very, very big, is this going to converge to anything meaningful? And stuff like that. Okay, so that's the kind of question we ask when we analyze a random walk on a graph. Okay, so we'll do many different lectures on random walks. Random walks actually also tell you a lot about graphs, right? So, but that'll be unveiled over the course of several weeks. Okay. All right. Now, in the context of a random walk, so in general, although the random walk is initially described as you're at a vertex and then you take a random step, but in general, at some point in time, you have some distribution over vectors. I could be here, over vertices. I could be here, I could be there, with various probabilities, right? And sort of from that distribution, I can take one random step. So maybe I have 10% chance I'm here and 10% chance I'm there. So maybe with 10% chance I go here and I take a random step, or 10% chance I go, I'm here, I take a random step. And that'll give me a new distribution for the next step. Okay, so random walks are really kind of outputting new distributions with each step. A stationary distribution means, okay, I'm currently some distribution over the vertices, and if I take a random step on that distribution, I get back the same distribution. So it's when it kind of reaches an equilibrium. Okay, that's the definition. So here's an example we've already done, so I don't need to highlight it. So before we said it was 1, 1, 1, was weights that would work, except now we need everything to sum to 1, because it's a distribution. So there's 3, so it's 1/3, 1/3, 1/3. Okay. So if I'm at any of these vertices with probability 1/3, and I took a random step, I will again be at any vertex with probability 1/3. Okay. All right, so in this language, we can take that previous theorem and restate it as follows. Every random walk has a stationary distribution, and if the underlying graph is strongly connected, then the stationary distribution is unique. Okay. All right. Okay. So, I guess the deep question is why. Okay. And I guess at some level, the answer to this question is linear algebra. Okay, so we're going to do a lot of linear algebra today. So what I want to suggest is that if we kind of understand certain basic principles of linear algebra, this will sort of come out for free. Okay. I know everyone's comfort level with linear algebra is at different levels, so we'll just go through it together and plug in holes as they come up. So just ask also questions, because maybe some people do this stuff all day and some people don't. Okay. Any questions? All right, let's start small. A function is linear if f of x plus y is equal to f of x plus f of y. Okay. All right. At some level, linear algebra says if you only know this about the function, how much structure do you get? The answer is you actually learn a lot. You know a lot about f if you just know it's a linear function. Okay. We'll see some of that. I'm going to present these as facts and it might seem boring, but I think it's amazing to keep in mind that at some level, we're starting with very little information and out will come a ton of structure that we can actually work with and get algorithms out of. So that's sort of the right perspective to have. Okay, so we're going to associate sort of with every graph, we can associate a linear map or a matrix. So every linear function can be expressed as a matrix. Okay. This is maybe slightly different notation than you're used to as an adjacency matrix. Okay. But for every edge from U to V, the entry AVU will be equal to 1, and otherwise it will be equal to 0. Okay. This way, the reason I have the coordinates maybe switch from what you're used to is I kind of want to think of, having, say, an input vector, putting 1 on E. So E sub U will be the indicator vector just for U. Okay, so that means that we have like 0 everywhere, except we have a 1 in the youth coordinate and 0 everywhere else. Okay. So I kind of want to think of like, oh, I have a 1 on U, and then I put it into A, and it sends it to across all the edges. Okay, so AEU will give me sort of the out neighbors of U. Okay. All right, so for example, in this notation, score 1, our first idea was just to count the number of edges coming into a vertex V. Okay, so at some level, if I did A1s, so this is the ones vector over V, okay, and I multiplied against A. So, okay, what will this do? So, doing EU against A on the other side is sort of going to get you the youth row of A. So that's listing all the edges coming into A. And then I'm multiplying that with the 1 vector. So for every edge going into U, you get 1 point. Okay. All right, fine. I guess another example was the out degree of a vertex U. So here I would plug in an indicator vector for U into A. So that will get me into the youth column. Okay. And if I wanted to count all the edges, I could sum them all up by taking the dot product with ones. Okay. All right, not too exciting. Almost at the random walk part though. All right, I'm going to let D denote the diagonal matrix that has all the degrees along the diagonal. Okay. Something like that. All right, so the random walks matrix is going to be defined as AD minus 1, but maybe I can break that out coordinate-wise. All right, so if I'm looking at the V comma U coordinate of R, okay, and we just did our kind of old-fashioned matrix multiplication stuff, okay, you're looking at A, B, W, D minus 1, W, U. Okay, so I'm summing over W, kind of zipping them together. I'm not sure what everyone's comfort level is. So if I'm going too slow, I'm sorry. If I'm going too fast, let me know. Okay, whatever. All right, so D is the diagonal matrix. So when W is equal to U, you'll get a non-zero entry. Otherwise, it's 0. So actually, this summation, the only relevant entry is the one where W is equal to U. And you'll get A V U over the out degree of U. Okay, so A V U is 1 if there's an edge, or 0 if not. Okay, so what R is really doing is if I plugged in like R times P, where P is a distribution over vertices, that's actually going to produce the distribution of one step of the random walk. Okay, so maybe I can make that a little bit more clear. So REU is sort of like I'm currently at vertex U, and then I apply R. So I'm taking one random step from R. Okay, and what we can see from this line we slowly did together is that if for each vertex V, if there was an edge from U to V, then it'll go there with probably 1 over the out degree, because you choose a random edge. If there wasn't an edge, AVU would be 0, and so you wouldn't be able to go to V. Okay, so for each vertex, REU will give you one random step from U. If you have a probability distribution, so that's like a convex combination of EUs for different U's, that'll kind of apply a random walk to a distribution and get you another distribution. Okay, so, alright, so, uh, right. So for example, score 2 of V, which was counting up the number of incoming edges divided by out degree or something, could be expressed concisely like this. Okay, all of the vectors kind of can give out 1 point, but they're getting divided down by the degrees. Okay, and an EV is just making you look at the Vth row. Okay, and then the definition of a stationary distribution is that if I have X and I take a random walk, so I apply R to it, Rx, I get back X. Okay. All right. So, okay. So this is really the important thing. Okay. So stationary distribution is something that satisfies X equal to Rx for some matrix linear function Rx. Okay. That's a very special kind of relationship. So whenever you have some linear map and you get AX is equal to lambda X, I'm sure you guys have seen these names before, and I'm sure it brings back happy memories. The lambda is called an eigenvalue, and X is called an eigenvector. Okay. Now, when I was first taught linear algebra, these were just like presented as like vocab terms, and I had to learn it and learn this thing. So I'm hoping today that we can at least imbue this with some like real meaning, because we'll actually be able to do something with it. Okay, so part of my goal is not just to expose you guys to some linear algebra, but to see why it's connected to something so you can actually remember it this time around. Okay. All right, so let me restate the theorem one more time from before in terms of random walk matrices. All right, so if I have some directed graph G and R represents that random walk matrix or linear map, then in our new language, we're saying that R has an eigenvector, X, that's non-negative, or it's a distribution, with eigenvalue 1. And if G is strongly connected, then X is a unique eigenvector with eigenvalue 1. Okay? And this is probably the format in which we'll prove everything for the rest of class. Okay? Any questions? I think there's going to be a lot of new vocab today, so today will be a little bit brutal, but at least we'll get it over with, and so next time it'll be less brutal. Okay. All right. Okay, so I'm just going to first go through some basics basic facts of eigenvalues and eigenvectors, where we won't really use the structure of a random walk initially, just to get ourselves warmed up and get some basic facts out of the way. And then we'll do the harder part. Okay, so we need to learn something about eigenvalues and eigenvectors. Okay, so our priority is not clear that eigenvalues and eigenvectors should ever exist. Okay, so this is a real lemma. The claim is that every linear map does have at least one eigenvalue and one with some eigenvector, although the eigenvalue may be complex valued. Okay. Does anyone know the proof of this? Some of you may have been exposed to this statement before. Or has anyone seen this before? Okay. 1, 2, 3. Do people feel like they vaguely might have seen it before? Okay, that's more typical. How many are sure they've never seen this before? Okay. Okay, that's totally to be expected. Alright, so okay. Alright, so here's sort of one way to prove this. There's different ways to prove this, but here's maybe the shortest. Okay. Let's see. Anyone know the fundamental theorem of algebra? It's exciting. Well, here it comes. Okay, so, I'm going to first fix any vector v. Okay, and what I'm going to take as a fact is that if you're in Euclidean n dimensions, any m plus 1 vectors is linearly dependent. Okay, the maximum number of independent vectors you can have is n. Okay, so I'm taking that as a fact. Okay, so in particular, if I look at the set V, AV, A squared V, so that means I'm applying A twice to V. ANV, okay, so I'm working at n dimensions here. That gives me n plus 1 vectors, so there must be a linear dependency. Okay. All right, so how can I write that? Okay, so what does that mean? So that means that there's some kind of set of coefficients, alpha 0, alpha 1 AV. They're not all 0. Where I'll get the 0 vector. That's not the 0 vector. Okay, that's what near dependency means. Okay, but that means if I look at this polynomial, okay, so that's a polynomial in X. P of A, V is equal to 0. Okay, so you can take a polynomial and plug in A and it just adds and multiplies the linear map. So if you take two linear maps, you add them up, you get a linear map. If you multiply linear map with itself, as long as the dimensions match, you get another linear map. In this case, the dimensions match. Okay, so polynomials are well defined. Okay, so so by the fundamental theorem of algebra, so do people know what the fundamental theorem of algebra is? Yeah, what is it? Yeah, okay, so every polynomial of degree n has n roots, right? So degree 2 has 2 roots. So x squared equals 1, x equals 1, or x equals minus 1. But also x squared equals negative 1. What are the roots? Imaginary I and negative imaginary I. Okay, so if you're in a complex plane, you do always have roots, and it matches. That means that you can write p of x as like, maybe here's the first root, here's the second root, All right, so should be n of them. Why did I write equals 0? Sorry. So you can factor p into the n roots. Okay, that may be complex. And now if I plug in p of a, v, then I sort of get something that's like a minus r1 times the identity matrix. So capital I's denote the identity matrix. So this map just ix is equal to x. A minus r2i is equal to 0. Okay. All right, so what have I shown? If I look at this, right? So at some level, okay, so we have some possibilities, right? If this is equal to 0, right, then that means that AV is equal to RNV. So that gives you one eigenvalue, Rn. But if it's not equal to 0, then you can move on to the next one, right? And if you might get something like A, if the next one then gives you the 0, then you would have gotten something like A times, well, I'll just write it this way. A times V prime is equal to Rn minus 1 V prime, where V prime is what came out of the first round. Okay, so eventually, as you move all the way down, one of these becomes 0, and the corresponding Rn will give you an eigenvalue. Okay, all right, sort of a algebraic proof. Okay, but that's important, right? It's important to establish that everything always has an eigenvector. That's not at all obvious. I mean, we have to use the fundamental theorem of algebra, which is not trivial. Okay, we have to invent imaginary numbers to find them. And I should point out, imaginary numbers don't quite help us out yet, right? Because what am I going to do? I want to analyze the websites and I have an imaginary eigenvalue? Like, that's not going to do me any good. All right. Okay. Another basic fact. Maybe we can do this quickly. A is invertible if and only if A transpose is invertible. So I should mention that A transpose is a linear map. Well, if it's a matrix, it's kind of rotating everything over. Another kind of definition is that if I'm taking whatever's the output of A transpose X and I'm taking the dot product with some other Y, it's always equal to if I had applied A to Y and then taken the dot product with X. Okay. All right. I personally almost never think of matrices and actual entries, and I always prefer these kind of algebraic things, but everyone's different. Okay, so let's quickly establish this because this is also a basic fact that we kind of need to eventually do our proof. A matrix A is invertible if and only if its transpose is invertible. Okay. So, okay. So let's say A is invertible. Okay, so there's some kind of A inverse. Okay, the claim is that A inverse transposed will give you the inverse of A transpose. So we'll do that. Okay, so I want to show that this is somehow equal to Y. Okay? What I'm instead going to show is that for any vector X, this is equal to the dot product of X and Y. So if that holds for all X, then Y must be the same. Okay? The reason being, well, whenever you have some transposes, all you do is you flip it over and then things work out nicely. So we'll just do that together. So I can flip over the first one. Right? And then I flip over the next one. And here I should point out that A transpose is A. So when I flip over, I get A minus 1, xy. And now things will annihilate each other like that. Okay? So not too big a deal. The other direction follows from actually, you can just use this and then apply the first proof. The A transpose is equal to A. Okay, so that's just a fact. All right, here's something a little more interesting. A and A transpose have the same eigenvalues with the same multiplicities. This is going to be important. And the reason I'm going through this is because when we analyze random walk matrices later, it's going to be sometimes convenient to look at R transpose. That'll come up. Okay, so, alright, so A and A transpose have the same eigenvalues with the same multiplicities. Okay. Alright, so one way to do this is that, so lambda is an eigenvalue, right? If and only if A minus lambda I x is equal to the zero vector for some non-zero x. Okay, that would be the eigenvector, of course, which is the same as saying that A minus lambda I is not invertible. Okay, so if you're sending multiple vectors to the zero vector, then you don't have a bijection, so you can't invert the function. Okay, because any linear function will always send 0 to 0. So 0 is already taken. So as soon as I send a non-zero vector x to 0, I have a function that can't be inverted. Okay. Consequently, additionally, A minus lambda I, well, okay, so that's the same from what we just proved, that the transpose of this is not invertible. Not invertible. Okay. And you can take the transpose inside those parentheses. A transpose minus lambda times the identity is not invertible. Okay, because the identity transposes the identity. And finally, that tells you that lambda is an eigenvalue of A transpose. Okay, all right, not too big a deal. Nice clean facts. Okay, so that tells you that A and A transpose have the same eigenvalues. That's not obvious. Okay. They have different eigenvectors corresponding to eigenvalues, but all right. Okay, so those are those three facts we need. Those are fairly basic. We have not used any of the structure of random walks at this point, so this is now where things start to get more interesting. As you can tell, because there's a lot more written. Maybe that makes it less interesting, I don't know. Okay, so before analyzing random walks, we're going to analyze a different class of linear functions that are quote-unquote positive. These are the ones where the matrices all have strictly positive entries. That doesn't actually capture random walks unless it's like a complete graph, but we'll figure out how to reduce to this later. So, okay, if A has strictly positive entries everywhere, all the coordinates are positive, it turns out that A has an incredible amount of structure. Okay, so I think this is one thing to keep in mind. So initially we're just analyzing matrices. What are matrices? They're just like grids of numbers. No structure. Very little you can say, although we do know there exists some eigenvectors. At least one. Right? We have some small observations, but they're not particularly useful. If I assume that this arbitrary set of numbers arranged in a grid, they're all strictly positive, then suddenly we have a ton of properties. Okay? So in particular, there's sort of this principal eigenvalue and eigenvector. So there's a eigenvalue lambda 1 corresponding to eigenvector x1, has lots of nice properties. So first of all, lambda 1 is going to be greater than 0, and it's going to be real valued. Before we had complex valued, which of course is not useful. It's going to be positively valued, and x1 is going to have strictly positive coordinates. x1 is the unique eigenvector of lambda 1. x1 is also the unique non-negative vector, such that ax1 is greater than or equal to lambda 1 x1. All other eigenvalues mu are smaller in the absolute sense. So lambda 1 is always the biggest eigenvalue. And every other eigenvalue is strictly smaller, even when I take the absolute value. And no other eigenvectors are non-negative. Okay, so this is quite a lot. I mean, point A is probably the most interesting thing. The fact that you even have a real valued eigenvalue and the corresponding eigenvector, everything is positive. Okay? And all we're assuming is that all the numbers in this grid are positive. Okay, so this is a very strong theorem. Totally a mathematical theorem, but it's very strong. It's called the Perron-Frobenius theorem. Okay. All right. So we're going to try to prove this awful thing. Okay. All right. So, and this will probably be the most mathematical moment in the class. It's just going to feel like a math class for 15 minutes. Okay. All right. Okay. So this is sort of a delicate proof, but it starts like this. We're going to let L be a set of all values lambda, so that ax is greater than or equal to lambda x for some distribution x. Okay. And then we're going to start proving some claims. Okay, the first claim is that L is non-empty. Okay. All right, how can I prove that L is non-empty? I just need to come up with some lambda and some x where this thing is true. I can't take all zeros because x has to be a distribution. But probably your next best guess will be fine. Okay, let's take x to be, come on. I'll say x is equal to 1 over n. So that's entry 1 over n everywhere. Okay. So I need to show that ax is greater than or equal to lambda x for some x. Yeah. Every coordinate is bigger. Sorry. Huh? A over 2? Oh, okay. Well, okay, so first of all, lambda needs to be, sorry, these should be values that are real values, not matrices. Okay. Okay, well, okay. Let's say, okay, so all the coordinates in AX, so since A has strictly positive values, I mean, all the entries are positive, and X also, it's just all ones. So every coordinate in AX is going to be something bigger than 0, right? So if lambda was anything bigger than like 1 over AXI for all I, or no, less. Sorry, no, what am I saying? Okay, so if lambda was less than the minimum value of these coordinates, then you'll be okay by a factor of n or something, right? All that matters is that all the coordinates in AX are positive, so you can just make lambda small enough so that lambda x is smaller than any of those coordinates. Okay, so that's not too big a deal. Wrong check mark. Okay, next part is to show that L is bounded from above and below, I guess. Okay, This one's a little bit harder to guess, so we'll just start. So I want to show that okay, it's bounded from below because all the values are non-negative, so 0 is already a lower bound. So all I need is an upper bound on L. Okay, so one way to do this is to say, okay, I'll start like this. If I just apply ones on both sides, this is some finite value. Okay, and if I take any distribution x, and now since A has strictly positive coordinates, if I take kind of 1 and I shrink it to something smaller like x, it's only going to decrease all the coordinates. Okay, so this is at least 1s times ax. Okay, and if you have some value lambda that is satisfied for this x, right? If lambda x was smaller than ax, that would be okay. And that's lambda. Okay. So for all values lambda, if x was the corresponding distribution that put lambda in L, then whatever this thing holds. Okay. So that gives us some upper bound of A1's A1 on L. Fine. The last thing to show is that L is a closed set. Okay, so for those who maybe haven't done much of this kind of mathematical argument with open and closed sets, what it means is that if I take any converging sequence of points, okay, so let's say, in other words, let me just put the definition. So let's say that I have some infinite sequence, lambda 1, lambda 2, coming from L, okay, and suppose that these lambda i's are converging towards some point lambda. I'll write lambda star. Okay, so there's some point, and I'm picking points out of L that's getting closer and closer. L is closed if lambda star is always in L. Okay, so an example of a closed set is if I have a closed interval, right, and I'm kind of gradually picking points that approaches the boundary. It's converging to the boundary, but since it's a closed interval, it also contains the boundary. Okay, so I need to show that L contains all of its limits. Okay, so if I have a sequence like this that's converging to some point x lambda star, okay, and let's say that x1 and x2 are those distributions that put the lambda i's into L. Okay, now delta, the distributions over n is also a closed set. You don't believe me? Okay, so because it's closed, bounded, and compact, okay, let me just go through it quickly to get over with. You know for a fact that these xi's are going to converge to some point x star. That's also in the closed distribution, in the set of distributions. So what you have, okay, this is just a formality, is that if I'm looking at ax star, this is the limit in I of these points xi, okay? And then, I mean, for those who are keeping score at home, when you have a linear function, you're allowed to take the limit outside of it, because it's continuous. If you don't care, that's fine. Okay, but if you did care, that's why. And okay, so there's a limit as I is going to infinity, axi. This is always every entry. We have this, and this gives us lambda star. Sorry, xi, and this gives us lambda star x star. Okay. All right. So that means L is closed. Okay. Doesn't matter too much. What matters then, if you know these three properties, okay, that implies that L has a finite supremum. Okay. Lambda 1. What does that mean? That means lambda 1 is in L, and it's bigger than all numbers in L. Okay, but it's important that it's in L. Okay, and then that means there also exists some x1 such that ax1 is greater than or equal to lambda 1 x1. Okay. All right, so that's all we know right now. And now the claim, we're not making very good time. The claim is that ax1 is equal to lambda 1 x1, and that's the eigenvalue and all that stuff that we're looking for. Okay, okay, I'm going to try to figure out how to do this much quicker. Okay, so here's what we're going to do. We're going to write, I'm probably just going to prove just like one of the properties in our theorem after all, and then try to get to random walks, and we'll move on with our life. Okay, no one's complaining. All right, so let's write ax1 is equal to lambda 1 x1 plus y plus y, okay, for some y out there. And I want to show that y must be 0, because that would force ax1 to be equal to lambda 1 x1. Okay. So if y is not 0, and in particular it's greater than 0 because it's already greater than equal, let's choose epsilon so small that epsilon divided by 1 minus epsilon is at most this quantity. Okay. Seems a bit obscure at the moment, but we'll make some use out of it. Okay. Now we have 1 minus epsilon x1 plus epsilon. Why did I say that? Okay. Okay. All right, so y divided by 1's y, I mean the sum of y's, is some distribution. So if I took 1 minus epsilon of one distribution and add epsilon of another distribution, I get one total distribution. Okay. And okay, we also have, if I apply a to this thing we just constructed, okay, then of course this is at least 1 minus epsilon ax1, because I'm just dropping one of the non-negative terms. Okay. And we already said that's equal to 1 minus epsilon a, lambda x1 plus y, which is at least, actually strictly greater than, lambda times 1 minus epsilon x1 plus epsilon over y, because that's how we chose epsilon. Okay. But that means I could have actually made lambda 1 a little bit bigger and still been in the set L. But lambda 1 was supposed to be the unique maximum. Okay, so that's the issue. Okay. All right, so what we've shown is that ax is equal to AX1 is equal to lambda 1 x1, where lambda 1 was originally just this maximum value in this special set L, and x1 was the corresponding thing that put it in there. And then at least, some of the other properties are easy. For example, we know that x1 is equal to 1 over lambda 1 ax1. If I divide it out, I know that ax1 has strictly positive entries because x1 is positive. Yeah. Okay, it's going to force it to be positive. And what else is there to say? Okay, I guess that's basically it. Okay, so what I want to do in the remaining 5 minutes is, okay, so in the notes you'll find the rest of the proof of the other properties, okay? So these other things are kind of okay too, but I want to spend the last time at least relating it back to random walks, and then we'll take this as given mathematical fact. Alright, so here then is the old theorem is here. Here's the new version. Okay, so I want to analyze in particular a random walk on a strongly connected graph. Okay, this was the original motivation. I want to say there's an eigenvector x that's a probability distribution with eigenvalue 1. I want to say that x is a unique eigenvector with eigenvalue 1. X is the only non-negative vector, and all other eigenvalues have mu less than 1. Okay, so if you can remember what we half proved previously, there's some correspondence between one set of properties and the other. Okay, but there's a big difference, which is why I would love to just apply that theorem directly to R. Okay, but what's missing? How come I can't apply that first theorem about positive linear maps to random walks R? Sorry? Huh? Well, that's true, but I guess, so the question is more that, okay, this theorem takes as input a matrix A. And I would love to just put R into the theorem, but I'm saying I can't. There's something invalid. I'm breaking a rule. What rule did I break? Yeah. Yeah, strictly positive. So we needed A to have all positive entries to do that proof from before. But R reflects a graph, right? So if there's no edge, that's just a 0. If there's an edge, it's 1 over the degree or something. But if there's no edge, there's a 0. Okay, so that's the more conceptual, maybe interesting question that's more fun to answer for you guys. Is how can I take R, which reflects a sparse graph, a directed graph, not necessarily a complete graph, and reduce it to something that has entries everywhere? Oh, add negligible edges? That could work. Yes, that ought to work, but it's not what I had in mind. Okay, that's possible. So we can have teeny tiny weighted edges, and then that'll get you some theorem, and then you can try to argue that as you make the weights go down to 0, you should be converging to the truth for the original matrix R, so to speak. Although there will be some delicacies in terms of arguing that taking the limit is okay, but I think that's okay from what I can tell. But I had a different idea that's maybe a little more combinatorial. Okay, so it's true that if I take kind of one step on the walk, there may be many zeros. Like imagine I'm starting at a vertex here, right? I can visit some vertices, but not all of them in one step. I need to be able to visit all of them to sort of have no zero entries, right? With some non-zero probability. So if I took 2 steps, my odds go up a little bit. And if I took 3 steps, it's sort of starting to diffuse, right? And if I go to n steps, so I can't necessarily argue that after n steps I could be anywhere. Because like if you have a cycle or something, maybe there's no choice and you're going to be in some specific spot after n steps. But I could argue, because the graph is strongly connected, that if I chose a number between 1 and n uniformly at random, some number 10, and then I took 10 steps, I could be anywhere. Because the graph is strongly connected. So there's a path between here and here with, I don't know, 100 edges. So I could have randomly chosen 100 and have a non-zero chance of getting there. Okay? So what we can do is we can look at the thing we want to prove is in the bottom right, if you can see it. So let's let B be sort of like the sum or the average of taking 1, 2, 3, 4, 5, however many steps. Okay. So since the graph is strongly connected, there's a non-zero chance from any vertex to get to anywhere within n steps is really what this is saying. Okay. That means that B is going to have strictly positive entries because B is saying exactly from this experiment, if I chose one out of n uniformly at random and I took that many steps, what are the odds of getting there? So I can apply the theorem to B, right? And the one thing nice is that if I have some eigenvalue, Rx is equal to lambda x, right? And if I apply that to B, okay, I'll get 1 over n okay. Something like that. So in particular, this quantity, the average of the lambda i's, is an eigenvalue of B. So there's some corresponding between the eigenvalues of B and the eigenvalues of R. It's sort of the sum of the average of the powers. Okay, so that's good. So one thing, okay. But another question is, why would there be an eigenvalue of 1? Okay. All right, so this part's kind of cute. Okay, so because R is a random walk, what happens if I look at R transpose times the all ones vector? This gives you, in fact, the all ones vector. Okay. Do people feel okay with this? So if I do R transpose ones, I'm going to sum up each row. Okay. And if I sum up all the rows, I get this backwards. Okay. Okay, but one sec. So let's keep going. Okay, so one thing important is that before we talked about how A and A transpose always have the same eigenvalues and the same multiplicities. So this implies that that 1 is also an eigenvalue of R. Okay. And then, what else is there to say? Okay, what was the last one to do? Okay, so now, okay. Okay, so now let's say that X is any eigenvalue, eigenvector of eigenvalue 1. This will be the last thing we prove. I just want to prove that X is non-negative. Okay, and if I plug this into here, okay, we get Bx is equal to 1 over n, sum of I is equal to 1 over to n, 1 to the I, which of course is just 1, times x, which is x. Okay. All right. So what does that tell us? That tells us that For B, X is an eigenvector of eigenvalue 1. Okay? But X is also going to be non-negative because of reasons left unspecified. Um, the only thing I'm missing is why this is a dominant eigenvector, but in principle, if we apply this past theorem to B, and then we had just identified our lambda 1, then everything else will follow. Okay? I'll just let you guys go because I think you guys are tired of this, but that was the main takeaway, is that we had the Perron-Frobenius theorem, which will give you a lot of structure if the matrix is completely positive, and you can reduce random walks to it by instead considering sort of these n-step random walks, 1 over n uniformly at random, and otherwise just double check with the notes to cross the T's and dot the I's. All right, thank you.